The title of this presentation is Quantum Inverse Scattering Type Objects for the Six-Vertex Model with Reflecting Boundary Conditions Encoded from the Skylanian Algebra. So to give an intuition and a direction for the second to last presentation in this series, we're going to just very briefly recall some information and material that was presented in the previous parts of this series and how this can exhibit some types of connections and the robustness of the methods that we have been studying and classifying in 2 and 3 dimensions. And in this case, because there are still some interesting characteristics and qualities of these models that in 2 dimensions that can be explored, we're going to restrict ourselves to a 2-dimensional case and look at a difference in the encoding of boundary conditions for the vertex model in this lower dimensional state space. And then we'll be able to come back to how 2 and 3 dimensions, the 6-vertex model and vertex models in general in 2 and 3 dimensions can relate to each other, and how that can help us further develop some interesting questions or directions of future research in the next presentation, which is in the last part of the series. And so from the previous presentations, we were introducing research areas within statistical mechanics, which are related to several previous works on, like we had mentioned, crossing probabilities or RSW, delocalization of the height function for 6-vertex models or vertex models in general could also be interesting, as well as integrability from the quantum inverse scattering method. And we introduced algebraic notions from the integer valued and set value tableau from Lasso and double growth and Dieck polynomials, which was related to the colored R matrices. And this is ultimately a very important feature and characteristics of the quantum inverse scattering type method, because it's related to the fact that this R matrix is going to satisfy and be a solution to the Young-Baxter equation. And the colored R matrix also satisfies Young-Baxter equation, as does the universal R matrix from the factorization, which we had mentioned and alluded to at several parts, and how that comes into play from a 3-dimensional quantum inverse scattering approach for triangular ice, or the 20-vertex model. And as we had mentioned, to further study other properties of such L operators, we introduced a change in notation for studying the large n limit of the 3-dimensional transfer matrix, which can also be of use for studying the asymptotic limit of entries of the quantum monodromy matrix. And because this part of the presentation, as the second to last presentation in the series, it's relating to a 2-dimensional encoding of boundary conditions, I thought that was particularly helpful and salient to actually draw the viewer's attention back to the system of 16 relations that we had discussed in an early part of the in early presentations and parts of the series, and how this related to having us look for richer type of algebraic structure in 3 dimensions. And we described all these connections from algebraic studies and algebraic notions and combinatorial notions, and even from representation theory in 3 dimensions. But there is even another type of connection which can be studied from an algebraic notion or from an algebraic type of perspective in the 2-dimensional case. And this is helpful because it's demonstrating how we can make use of some type of minimalistic type assumptions and be able to describe very quickly in even the shorter part of this presentation of this series how other types of objects can be defined depending upon the boundary conditions, and how this can relate to even other questions and problems in statistical mechanics, which seek to establish some type of quantification or some knowledge base of how the boundary conditions of different models are impacted, and whether certain classes of results or types of results would still be expected to hold if the boundary conditions were different and changed. And so this is to say that in 2 dimensions, a number of Poisson brackets that are to be approximated depend only on the 4 entries from the 2x2 transfer matrix and the 2x2 quantum monodromy matrix. And this is important because it's relating to the expressions that we obtain for multiplying L operators together, which we had also discussed very thoroughly and very extensively, how this relates to the direction of the arguments that we have to take for a QISM type approach in 3 dimensions. And so the expansion of the 2-dimensional transfer matrix from the large n limit was given by a product of L operators, which we're trying to determine recursively what are each one of the entries that appear in the 2-dimensional transfer matrix. And as we had discussed in other parts of the the series, like the sixth video and the seventh video of the series, we described how we can introduce some type of reformulation from a three-dimensional L operator, which holds up to Dynkin automorphism, and how this family of L operators opens our perspectives more broadly rather than just a discrete probability perspective, because we can make use of some type of basic or very minimalistic type assumptions from a discrete probability perspective, and be able to look at how one would encode different properties of this probability measure for the 6-vertex or the 20-vertex models in higher dimensions, and how that would relate to algebraic characteristics like we had mentioned from those special types of polynomials. So the presentation overview for this presentation in the series is that we want to demonstrate the significance of encoding boundary conditions in the 6-vertex model. And in doing this, we'll exhibit algebraic properties of the model from the two-dimensional state space. And like we had mentioned, this was different and unlike the algebraic connections that were previously described from the three-dimensional state space. And one of our main goals will be to establish continuity with the last presentation of the series. Like we had mentioned, this is the second to last presentation of the series, so we're winding some things down about what we had already talked about across several other presentations in the series, in which we had started out with some types of general notions of integrable probability and how that related to some of my previous preprints, and how these previous papers and these previous projects, they allowed us to question how we can expand on our notions of integrability or discrete probability or thermodynamics or even equilibria, or different stages or different phases of the phase diagram, sectors of the phase diagram, and even conformal field theory. Because we know that the 6-vertex model, it has a conjectured phase diagram into ferroelectric or anti-ferroelectric regions and behaviors which can relate to other models in statistical mechanics in which we can look at the presence of disorder or order. So this is just helping us be able to broaden our perspective a little, as this is the second to last presentation of the series, and being able to describe very briefly how some objects, they can directly carry over, which could make different types of boundary conditions and different types of assumptions on the types of configurations that we would like to allow in a finite volume for the 6-vertex model or other vertex models to be of interest. So the reference paper that we're going to have for this part of the presentation in the series is that we want to look at this paper from 2019 in mathematical physics that's titled from these two authors, Boundary Conditions for the 6-vertex Model Reflecting N Boundary Conditions. So as we had discussed earlier in the presentations in this series, there are many different types of different boundary conditions, whether you can look at Russo-Seymour-Welshin crossing probabilities under sufficiently flat boundary conditions, and look at how certain parts of this arguments would not be able to extend over to study the 6-vertex model with a height function that has some slope to it that lies within the interior of the set of rational points that we had described in the first presentation in the series. And in this case, the 6-vertex model, there are even other classes of boundary conditions that are of interest for the 6-vertex model, because the reflecting N boundary conditions relate to the Skylanian algebra, which is an algebra that's defined in this paper, and it's even given in many other types of references that are separate from discrete probability. But the algebraic notion for this two-dimensional model in this particular class of boundary conditions, it exhibits how it could be of interest, as we'll also talk about in the next last presentation of the series for challenges and prospects, how boundary conditions can impact different types of results and characteristics of the 6-vertex model, and how that would still be related to the objects that we introduced and we analyzed and made sense of for the quantum inverse scattering type method. And so the objects that the authors introduced on this paper, as should not come as a surprise, is that we look at the transfer matrix, which are given by these 4 blocks, as well as the disorder parameter, which we had also introduced, which is used to segment different sectors of the conjectured phase diagram for the 6-vertex model. And so the R matrix is given by a very similar formula that we gave for the R matrix that we use for discussing how the Hamiltonian flow in the presence of inhomogeneities for the 6-vertex model can be shown to satisfy an integrability property. And it's given by the fact that from the entries in this R matrix, we can define operators which are corresponding to each one of the entries, the non-zero entries which appear in the R matrix, by given that which are respectively given by big A, big B, big C, and big D, which are also still a function of the spectral parameters lambda, which are given, which the transfer matrix from the previous slide is also dependent on. And then with this framework, the authors are able to make use of the types of objects that we had introduced for the quantum inverse scattering type methods in 2 dimensions and in 3 dimensions for the triangular ice. In this case, for the 2-dimensional 6-vertex model with reflecting boundary conditions, because they begin by computing in several technical computations, several expectation values by taking various products and elements of the transfer matrix. So this is given by the fact that we can have a ket state. In this ket state, it originates from quantum mechanics because they look at time evolving states and states of quantum systems which live in some Hilbert space. And in this case, we're looking at a product of this state, of this up state, with some fixed number R entries of the B sector of the transfer matrix. And then we're also multiplying by another term which is given just dependent upon lambda instead of lambda sub j from R lambda parameters in this product preceding the ket state. And the elements of the K matrix also come into play because they're obtained element-wise from the following formula, in that we look at the big K matrix like we recalled that we had introduced for the lower and higher rank spin chains. And in this case, for the 6-vertex model with the reflecting boundary conditions, which, like we had mentioned, is mentioned in this paper that we're putting a little bit under the rug currently, but it's just relating to a Skylanian algebra, which is an algebra, and as any type of algebraic object and system, it's dependent upon generators and different sets of relations that these generators would satisfy given an action of elements within this algebra. And in this case, we can encode the boundary conditions by taking some real parameter xc and taking plus or minus lambda and dividing just by the sign of xc. So this gives a way to define the element-wise the two non-empty boundary contributions from K plus and K minus, and then the two elements in the K matrix along the anti-diagonal will be 0. So this is given an explicit formula for the two entries of the K matrix that are going to be responsible for enforcing the reflecting boundary conditions for the 6-vertex model in 2 dimensions. And coincidentally, even the form of the 6-vertex weights come into play even in a similar different type of way, like how a formula for the weights from the L operator in 2 dimensions can be used to establish some type of integrability condition for the inhomogeneous Hamiltonian flow, because the form of the 6-vertex weight under reflecting boundary conditions share many similarities with the terms that were manipulated for the 2-dimensional quantum inverse scattering type approach. So what we have is that, as we had for the K plus and minus terms, which denote the 2 non-zero entries which are given in the K matrix, these weights can also be defined that are a function of the spectral parameters lambda j and mu sub k, and they also have a subscript, a plus and minus, to denote that we can have different types of boundary conditions which are enforced for different portions of the finite volume. And this is given by the fact that the first weight, which is given by the 6-vertex model that the authors from this paper reference that we've been discussing in this presentation, they look at with reflecting boundary conditions, it has a 2 eta term, which very much parallels and reflects the term in the 2-dimensional L operator that we had introduced for reflecting or for domain wall boundary conditions due to Colombo and Pronko, which had a sign of a 2 eta term, as well as a poly z basis, a sigma z term that's given in the sign. So it's very much reflecting a similar type of weight, but it's demonstrating how a modification to the domain wall boundary conditions in the 6-vertex model can be used to obtain interpretations and conclusions about reflecting end boundary conditions for the 6-vertex model. But besides the first weight, which is given by the A term, the B term is also given by a similar type of expression, which doesn't have the plus of 2 eta term, which is appearing as an additional argument in the sign function in the first weight. And then finally, the C term is just given by sign of 2 eta. So in comparison to the similar groups of terms which appear in the L operator for the two-dimensional case, for this case, for the six-vertex model with reflecting boundary conditions, there's a little bit of a difference because the polybasis elements that we have to manipulate very carefully when we're applying the two-dimensional quantum inverse scattering approach, they don't come into play in this class of reflecting boundary conditions, but the formula in the expressions and how they relate to one another and the types of interpretations about the vertex model and the influence of boundary conditions, they're still very clear and easy for us to interpret at this point in the series with the types of notions in 2 and 3 dimensions that we've been developing. And the authors also provide an example of a finite volume with reflecting boundary conditions, which is given by the fact that they have three spectral parameters which are defined in each direction. And if we look at these lines that are going up and down, they're given by specifying spectral parameters mu1, mu2, and mu3. Whereas for the other types of spectral parameters, lambda1, lambda2, and lambda3, they can enforce reflecting boundary conditions because one orientation of the boundary that's pointing inwards is given by lambda I. But the thing is that as the path travels around, if it were to reach the position of the minus lambda I that's given here, it would actually have an opposite orientation. So we reflect that opposite orientation by introducing an opposite sign on the spectral parameter lambda1 at this other part of this connected portion of the finite volume. And we can also do the same for lambda2 and lambda3. So, excuse me. So this is exhibiting one potential type of characteristic of the reflecting boundary conditions and how these boundary conditions can be enforced in finite volume. And this is also going to relate to another example of a finite volume and how the boundary conditions can be enforced with a reflecting edge that informs how the quantum monodromy matrix and the transfer matrices can be used to study a different class of boundary conditions for the six-vertex model. And so the entries of the two-dimensional transfer matrix with reflecting boundary conditions can be expressed in terms of an action of a T and a twiddle T operators on the K matrix. So this is to say that we have some K matrix, which, like we said, it's a 2x2 matrix, and we have these two entries which are given by the plus boundary conditions and the minus boundary conditions, and then the terms which are given on the antidiagonal, the 2x2 matrix, are 0. So from the two non-zero terms that we would like to obtain, we can perform a type of conjugation. It's almost like a linear algebra type of transformation on one matrix, namely the K matrix, to obtain another 2x2 matrix from the T of lambda and the twiddle T of lambda operators, which is given by script A of lambda, script B of lambda, script C of lambda, and script D of lambda. And as we had mentioned, there are two potential orientations for reflecting boundary conditions, which is given by the fact that, like we had mentioned in that previous diagram that was reproduced from the paper reference from these two authors, they can study reflecting boundary conditions and make sense of these types of classes of boundary conditions, or this type of class of boundary conditions, by making use of quantum inverse scattering type approaches, but being able to use this minimalistic set of assumptions in very few objects for a completely different interpretation, which can relate, as we'll mention in the last presentation of the series, how there can be many connections of interest for two-dimensional and three-dimensional approaches from the objects that are introduced for a quantum inverse scattering type approach. And this is given by the fact that one orientation for the boundary conditions at the reflecting edge can be kappa plus or kappa minus with the opposite orientation. And as we had mentioned, here's just an explicit form of the K matrix for encoding reflecting boundary conditions, in which we said there's one kappa plus term and a kappa minus term, and there are two other zero terms on the anti-diagonal of this 2x2 matrix. And this is an example of the configuration over 4 edges, which is enforced with reflecting boundary conditions. And it's pretty closely related to the other type of configuration that we had given earlier, in which we had those three interconnected pieces, which had the spectral parameters minus lambda1, lambda1, minus lambda2, lambda2, and minus lambda3, lambda3. In this case, because we're just looking at a finite portion of the square grid, we can have 4 spectral parameters because there are 4 horizontal and 4 vertical lines. And then we also have 4 spectral parameters, lambda1 through lambda4. And this is given by the interesting fact that the boundary conditions are reflecting and they have a reflecting edge, because it's almost like a domain wall boundary conditions. But like we had mentioned, it's a little bit different because these types of boundary conditions, they reflect off one another when we're looking at different portions of the finite volume and looking at just the orientation of the edges that are along the boundary of the finite volume. And we proceed to study the quantum monodromy matrix from information on the transfer matrix. And this is very much a hallmark of the two-dimensional and three-dimensional quantum inverse scattering type methods, because we look to perform subtypes of computations from maybe multiplying L operators together, whether it be two-dimensional or three-dimensional L operators or other types of expressions together. And then how this would provide us any type of information on a set of relations or certain properties that would be satisfied by the quantum monodromy matrix. And so the quantum monodromy matrix, it's still an object of central study in this case, because it helps the authors be able to classify information and properties of various expectation values and products of entries of the transfer matrix, and how that carries over to their interpretation of the reflecting boundary conditions, as well as the quantum monodromy matrix. And the authors also study the falling expectation value, which is related to the polarization. So in a similar way that we had described how the authors began several technical computations from an expression given by a ket of an upstate multiplied by various operators, which are given by entries of the monodromy matrix under different spectral parameters lambda sub I, with wherein the product I was going from 1 to R. There's also another type of expectation value, which they can normalize in the partition function of the six-vertex model under reflecting boundary conditions z sub n, where n is the length of the finite volume in one direction of freedom of the square lattice. And you can look at the bra state of a the bra of a down state multiplied by a whole bunch of entries of the operators from the transfer matrix, as well as another term which is given by the ket of the upstate. So this is to say that having different types of relations from the entries of the quantum monodromy and transfer matrices can come into play for computations in analyzing different kinds of boundary conditions for the six-vertex model, rather than just inhomogeneities or staggering. And a homogenization procedure can be introduced for the six-vertex model, also in the case of reflecting boundary conditions for the van der Maan determinant. And we're not really going to define the van der Maan determinant, but it's just very important and related to determinantal point processes and several other models in integrable probability that we haven't mentioned in this series. But in this case, the homogenization comes from the fact that we project all of the spectral parameters psi1 up to psi big N to 0, as well as the fact that the collection of spectral parameters mu1 up to mu big N all are sent to mu. So this is very much related to how we also discussed at earlier presentations in the series, how the presence of homogeneities or inhomogeneities can reflect in either positively or negatively on certain properties of the vertex model that we would like to study and classify further. And so the concluding remarks that we want to finish this second to last presentation of the series with is that we provided a brief overview of different boundary conditions which manifest algebraic connections in the two-dimensional vertex model that will be further discussed in the last presentation of this series, namely some open questions and directions of interest. And we introduced several models relating to the Skylanian algebra, in addition to how the reflecting end boundary conditions are enforced in finite volume through a couple examples of configurations which have different orientations from the reflecting end, and how this relates to the definition and boundary conditions of the six-vertex model. And as the last bullet point says, we mentioned a few directions of interest for future work that will be further described with connections to several variants of QISM types approaches. And thanks for watching.